In the previous lecture, we talked about how to find the surface integral and also how to find the flux for the vector field for a given vector field. We now have some examples. We have two examples about finding the flux for a vector field over a surface. Okay. In the first one, it says find the flux of the vector field F across the surface sigma. Sigma is the surface. This is the vector field, and sigma is given by this. This is the surface. That means here we are going to find the flux for F over that surface over Z equals 1 minus x squared minus y squared. Above the xy plane oriented by upward normals. Here we have these rules. Let me check. And this is the rule for finding. This is the rule for finding flux. Okay. Here we should find n. N is the normal vector. This is a normal vector. How to get the normal vector? We can get it from the surface. From the equation of the surface, we can get the normal vector. How? We say the normal vector, we first should find phi. We say we should find phi of xyz. And then we find its gradient. And then its gradient is going to be the normal vector. First, we should find phi. We say phi of xyz. Here we have given the surface as the equation. As you see, it's given that z equals 1 minus x squared minus y squared. Yeah, it's this case. It says if z equals f of xy, if this is the sigma, then phi of xyz is z minus f of xy. This is phi of xyz. Then we find gradient for phi to get the normal vector. After finding the normal vector, we can get the flux. Okay. Let's see here. For the first example, for A, we say here f of xyz, so f of xy, which equals to z, equals to 1 minus x squared minus y squared. And from f of xy, we can get phi of xyz. We say in the case if z equals to a function of xy, we say phi of xyz equals z minus f of xy. Here f of xy is 1 minus x squared minus y squared. We just replace f of xy by 1 minus x squared minus y squared. So you get z minus 1 minus x squared minus y squared. And so phi of xyz equals z plus x squared plus y squared minus 1. This is phi of xyz. And here we find n. N is the normal vector. You see n equals, look, let's first write down the rule here. See the double integral of r of, let's say here, since our surface is given by a function of xy, so we find the double integral over the xy plane. XY plane. For f dot n dA, here we just find the double integration over the projection of the surface. And the projection is on xy plane because z equals a function of f, a function of xy. Here we should find n. F is given. F is given in the example. F is the vector field, and n is the gradient of phi. To find the gradient of a function, we say it equals to a partial derivative of the function with respect to x times I plus partial derivative of the function with respect to y times j plus partial derivative of the function with respect to z times j times k, sorry. Here, this equals to phi sub x times I plus phi sub y times j plus phi sub z times k. This is the normal vector. So now, this is phi of x, y, z. We find the derivative, the partial derivatives for this function with respect to x, y, and z, and we multiply them by ij, and then finding the sum of them. Here, n equals, what's phi sub x? This is phi. What's phi sub x? Find the partial derivative for this function with respect to x is 2x. It's 2x I plus 2y j. Here is a partial derivative of phi with respect to y. Then phi sub z is 1. It's only z. It's k. This is the normal vector. And you also have given f. F is xi plus yj plus zk. Xi plus yj plus zk. Here we find the dot product of these two vectors. The dot product of these two vectors is multiplying of the similar components. I mean, I by I, j by j, and k by k. Okay, we say the double integration of r of xy for f times n dA equals the double integration of r xy for what's f? F is xi plus yj plus zk dot n. N is 2xi plus 2yj f should be given in the exam. Yeah. And you should find it. Here we have given the surface. From the surface we can get phi of x, y, z. Okay, this is phi of x, y, z. And from phi of x, y, z, that's it. From phi of x, y, z, we can get n. You see, n is the gradient of phi, which is phi sub xi plus phi sub yj plus phi sub z k. That's how to get n. And f is given, we just plug into the integration plus k. Okay, this is, sorry, in f, yeah, no, it's only yj. No, it's yj. That's it. No, it's next example. And then this equals to, here we multiply first component to first component, which becomes 2x squared. It's the double integration r of xy 2x squared plus y component to y component, which is 2y squared. Then z times k, which is z. Okay, and here this is dA. Z is a function of xy. Since we have double integration, so we must have only two variables in the integration. But z is given as a function of xy. As you see in the example, it's given that z is 1 minus x squared minus y squared. So you replace z by 1 minus x squared minus y squared. This equals to double integration rxy for 2x squared plus 2y squared plus z. Sorry, z is 1 minus x squared minus y squared. 1 minus x squared minus y squared. This is dx dy. Okay, it's dx dy, and this equals to the double integration of r xy. This is the projection r of xy. Here 2x squared minus x squared is x squared. 2y squared minus y squared is y squared plus 1 dx dy. Let's draw the graph of the surface. Let's draw the graph of the surface. The graph of the surface, it says z equals 1 minus x squared minus y squared. It is a paraboloid. It's upside down paraboloid. Okay. This is one. This is one. Okay. This is an upside down paraboloid. It says above the xy plane. Look, this paraboloid is going to down more and more, but it says above xy plane. So it's from this circle to above. And the projection is the circle which is on xy plane. This circle, let's take, this is the projection of that paraboloid on xy plane. This x, this y. It's only this circle. Okay. This is the projection. This is r sub xy. This is the projection of xy plane. And here it's 1. Okay. Theta here is from 0 to 2 pi. Okay. And r is the radius for the circle. Radius for the circle is 1. The radius is 1. Okay. And here we say this equals double integration. We convert the double integration to polar form to get the integration easier. Here x squared plus y squared becomes r squared. Here r squared equals x squared plus y squared. Dx dy equals r dr d theta. Okay, we replace x squared plus y squared by r squared, and we replace dx dy by r dr d theta. And then we write down the limits for the integration. Let's first write down the function, then we will write down the limits for the integration. This note. This equals to the double integration for r squared plus 1 r dr d theta. And r is from 0 to 1, is it? R is the radius for the circle. Let me make it bigger. We have this circle, its radius is 1. This radius is 1. So r is 1. R equals 1. And theta is from this angle to here. That is from 0 to 2 pi. Is it? So the limits for the integration, first we have the r, that means from 0 to 1, and then d theta from 0 to 2 pi. Here we find just this double integration. It's easy. This equals, first we multiply this r to the bracket, we get the double integration from 0 to 1, from 0 to 2 pi for r cubed minus plus plus r dr d theta. Now we first find the integration with respect to r, and it becomes the integration from 0 to 2 pi for r to the power 4 plus r squared over 2 from 0 to 1 d theta. We still have an integration with respect to theta. Because it's r, we take an integration, and it equals to 1 over 4 plus 1 over 2 is 3 over 4. This equals to the integration from 0 to 2 pi for 3 over 4 d theta. Now we take another integration for this one. This equals to 3 over 4. Sorry. This is 3 over 4 theta from 0 to 2 pi. And this equals to, we replace by 2 pi, then by 0. When we replace by 2 pi, we get 3 over 2 pi. This is the result. Okay. This is the flux for that vector field over the given surface. Okay. So here the most important thing here is to find and the normal vector. The normal vector can be obtained from phi, and also phi can be obtained from the surface. Okay. And then also converting the double integration to polar form and writing down the limits for the integration. That's all. Okay. It's for the first example. Now we have another example. In the second one, we have, it says, find the flux for f of x, y, z, which equals to xi plus 2yj plus zk. That's passed through the surface given by, this is the surface. This is the surface. And cut by x equals 0, y equals 0, and z equals 0. In the first octant, if we want to find the double integration of in the first octant, means the projection is in the first octant. The projection is in the first octant. So the first octant is xy plane. Here we say z equals, this is, let's first write down the given information. B. It says f of x, y, z equals xi plus 2y plus zk. F equals xi plus 2yj plus zk. And y plus 2x plus z, this is sigma. Y plus 2x plus z equals 1. It says in the first octant, that means the surface equation must be y equals to a function, sorry, z equals to a function of xy. Z must be a function of xy. This equals, sorry, this equals to 1 minus y minus 2x. This is it. This is the surface equation. Since this is the surface equation, what we do here, we are going to find n. N is grad phi, but phi is z minus, this is f of xy. Z minus f of xy. Okay, that's it. Now, here we say phi of xyz equals z minus z plus y plus 2x minus 1. This is phi. Then n equals grad phi, which equals to phi sub xi plus phi sub yj plus phi sub zk. That's all. Okay. Now we are going to find n, and as phi sub xi is find the partial derivative for this function with respect to x, then multiplying by I, we get 2i plus j plus k. This is n, and we have f also. We write down, we say flux equals the double integration of r of xy for f dot n dA. Let's write down the limits for the integration. Here we say, since we have a function of xy, that means if z equals 0. To find the limits for the integration, we let z to be 0, and we get that if z to be 0 here or here, we get y plus 2x equals 1. We always find the limits for the integration from the surface. Okay, we don't find from the vector fields. And then here y equals 1 minus 2x, is it? But it's given that y equals 0 also. That means y is from 0 to 1 minus 2x. And if y to be 0, then x equals a half. That means x is from 0 to a half. So y belongs to 0 to 1 minus 2x, and x belongs to 0 to a half. Here it's given that x, y, and z are 0. X and y are 0 here. So you just find another value for x and y. And here, y is a function of x. Y is from 0 to a function of x.
Why would we find another value for x and y if they are given
For the limits for the integration.
but they are given 0?
Yeah, it's given that it's one of the limits for the integration. We are given only one value for x, but when we take integration with respect to x, we must have both lower and upper limits. Okay, so we must find the other limit of the integration. X is from 0 to a half, and y is from 0 to 1 minus 2x. Since y is from 0 to a function of x, that means we must find the first integration with respect to y. Okay, then the second integration with respect to x, because x is from a constant to another constant. I'm just going to write down the double integration with their limits, then find the double integration by ourselves. Here, the double integration, x is from 0 to a half. It must be the second integration because it's from a constant to another constant. If both are from a constant to another constant, it's okay if you find any of them first. And it's from 0 to 1 minus 2x. What are the functions f and n? F is given. F is xi plus 2yj plus zk. And n is 2i plus j plus k. We just multiply these two. We get, I'm just going to multiply them. It becomes 2x plus 2y plus z. But here, z, let's check. We have z also. Z is a function of xy. It's a function of x and y, which equals to 1 minus 2x minus y. We replace z by its function. Yeah, it is from 0 to 1 minus 2x, and from 0 to a half for 2x plus 2y plus z is 1 minus 2x minus y. This is dy dx. Here we simplify this. It's minus 2x with 2x, I cancel out. Minus y with y, it becomes y. We get y plus 1, double integration from 0 to 1 minus 2x, from 0 to a half for y plus 1 dy dx. And I leave this for yourselves. It's easy to find that double integration. First, we take the integration with respect to y. Then we put the limits, and then we find the limits, the second integration with respect to x. That's all. Okay, is that easy? Now we have piecewise surface integrals. For the piecewise surface integrals, we find two flux, and then we find the sum of them. If we have piecewise surface integrals, we find each separately, and then we find the sum of them. As you see, here we have given an example. It says find the flux of flow for the vector field. Here we have given only one vector field. We find this vector field, I mean the flux for this vector field, of both I mean piecewise surfaces. Spreading through the piecewise surface sigma involving three surfaces here, x equals 0, z equals 0, and x equals 1. Here it is the first one, I mean, and it's in the first octant. It says in the first octant between y equals 0, y equals 3, and top by z equals 3. And top by z equals 3. So from both, z is from 0 to 3. Okay, z is from 0 to 3. Is it? And x in the first one, is in both. In the first one, x is from 0 to 1. First, it's in the first surface. Then in the second, y is from 0 to 3. The second. Look, in the first one, we have only x and z. We have only x and z. We have no y. If you have no y, so the normal vector can be obtained directly from this. We say the normal vector is only j. It's only j. It is only j because x and z are constants. Okay, but y is not given. When we find phi, we say in the first case, for the first one, as we have only x and z, say phi is y minus f of xz. F of xz is a constant. It's a constant. I have given constants for x and z. And y, so phi sub x equals 0. Phi sub y equals 1. And phi sub z equals 0. Because here it's a constant. The derivative of this function with respect to y and z. So x and z is 0. And the partial derivative for phi with respect to y is 1. It's 1. So here we say n is phi sub xi plus phi sub yj plus phi sub zk. So n is only, this is 0, and that's 0. We get only 1 j. See, this is n. Okay, if you have given the values for x and y, x and z, and you have no y, that means it's only j, the normal vector. So what if you have no y? What if you have no x? If you have no x, means it's only I. It's only I. The normal vector is only I. Here, for the first one, let me write down the flux. And so the vector field and surfaces. F of x, y, z. Let's solve it. We have f of x, y, z, it's capital F, equals, it equals to xi plus 2yj plus 3xk. This is the vector field. And for this vector field, we have given that x is from 0 to 1 and z is from 0 to 3. We have given this. Okay, we have given this. And since we have no y, that means the function of the surface is a function. So the surface is a function of x and z. And here we say sigma y equals a function of xz. It's a function of xz, and the function is a constant. And phi of xyz equals y minus f of xy. So f of xz. And so here we find n equals grad phi, which equals to phi sub xi plus phi sub yj plus phi sub zk. Here we find this is a constant function. And here phi sub x and phi sub z is 0 because we have no x and z in the function. But phi sub y is 1. So n is only j, is it? This is 0 and this is 0 also. And we just get 1 for phi sub y. We multiply it by j, we get j. This is n. And we have f also. Let's find the double integration here. This equals to, we have given both limits for x and z. X is from 0 to 1 and z is from 0 to 3. Both are constants. You are free to take any of these first. Okay, here I put dx first, then dz. May someone else take dz first and then dx. It's okay. Both are true, and this we will get the same result. It's f dot n. N is only j, and f is this. Let's multiply them and let's find the dot product of them. This equals to the double integration from 0 to 1 and from 0 to 3. For f is xi plus 2yj plus 3xk dot 0i plus j plus 0k. We multiply I by I, k by k, and j by j. We get only 2y. This is dx dz. This equals to the double integration from 0 to 1 and from 0 to 3 for 2y dx dz. That's it. Here 2y is a constant. This is for the first one, for the first part. Then for the second part, we find the same, and then we find the both double integrations to get the result, the sum of them. Here it says in the second one, we have given that y is from 0 to 3. But we already know that z is from 0 to 3. So y is from 0 to 3 and z is from 0 to 3. Here we have no x. We have no x. That means the normal vector is only I. The normal vector is only I. Yeah. Say for y from 0 to 3 and z from 0 to 3. N is only I. We do the same as we did before to how to get n equals j in the previous step. Okay, yeah, we got that n equals j. Here phi, because phi equals x minus f of yz. This is a constant. If it's a constant, then phi sub x is 1, phi sub y is 0, and phi sub z is 0. So you get I. This is n. And then the double integration for, let's take y first, from 0 to 3, and z from 0 to 3. For f dot n dy dz this equals to the double integration from 0 to 3 and from 0 to 3 for xi plus 2yj plus 3xk dot I plus 0j plus 0k. As you have no j and k, means their coefficients is 0 are 0. Dy dz. Then we find the dot product of these two vectors. We just multiply each components to the other component. I mean, all the similar components here. Xi multiplying by I is only x. we get the double integration from 0 to 3, from 0 to 3. For x, it's for x and dy dz. That's all. Now you have these two. So the flux is it's 1 and 2. The flux is 1 plus 2. 1 plus 2. We find the sum of both cases. This equals to the double integration from 0 to 1, 0 to 3 for 2y dx dz plus the double integration from 0 to 3, 0 to 3 x dy dz. Find the sum of these two double integration. It's easy to find. Okay, so the most important thing here is to know if it's piecewise, that means you have more than one double integration. You find the sum of all. You find the sum of the double integrations, which will be the flux for the vector field over the piecewise surface. Okay. Do you have any question? You have only this example. Let's finish this. Okay. I'm just gonna finish this example and it will be finished. Okay. Then I'll give you the grades. I'll share the grades with you. We have divergence theorem. For divergence theorem, we say let G be a solid whose surface sigma oriented outward. F of x, y, z, this is the vector fields, where P, Q, and R have P, Q, and R are the coefficients of x, I, j, and k. Have continuous first partial derivatives on some open set containing G. And N is outward unit normal. Yeah, it's unit normal. It says here the double integration over the surface for f dot n ds equals the triple integration. Look, it becomes triple integration. It becomes triple integration here for finding divergence. And when it says use divergence to find the flux, we must have triple integral. But in the previous method, we had only double integral. But when we use divergence, we must have triple integral. Okay. It is the triple integral over the region G for divergence f dv. And divergence of a vector field is the gradient dot the vector fields. Yeah, we find this one. We find the triple integral of grad dot f dv. That means we find the gradient of the vector field over the region G. Here, the most important here is to know how to find the limits for the integration. The limits for the integration. Here, we have this example. It says use divergence theorem to find the outward flux of the vector field. That's it. This is the vector field. We have given the vector field. It says across the surface of the region that enclosed by the circular cylinder. Circular cylinder. Okay. Here we use since it's given as a cylinder. It's easy to convert to cylinder form. Then finding cylindrical integration. I mean, then finding the integration. X squared plus y squared equals 9. Look, let's draw the graph. So x squared plus y squared equals 9. It is like this. It's 3. Its radius is 3. It's going to up and down. Okay. This is the graph. Yeah, this is the graph. And it says, and the plane is z equals 0 and z equals 0. That means it says the surface is bounded by this cylinder and z equals 0. That means from here to z equals 2. Let's say it's 2 till here. So here we find the double integration over this part of the surface. It's cylindrical. Okay, here I'm just gonna delete this. We don't need this. We just find the double integration over this surface. It's cylindrical. X squared plus y squared equals 9. It's a circle over xy plane, and then we expand it over, through z in the direction of z axis. And it also says that it's bounded by z equals 0, which is the xy plane, and z equals 2. It's bounded by those two planes. So the surface is this one. Now, it's important to find the limits for this integration, for the triple integration. We say the flux is here, that's it. The flux is the triple integral over G for grad F dV. It's volume. Okay, as you have triple integral means it's volume. If you have double integral means it's area. Here, to find the limits for the triple integration, z is from 0 to 2. Z here, we must convert this to cylindrical form. In the cylindrical form, we have dz, dr, d theta. We must have r and theta. So what's the radius of this cylinder? It's 3, because it is x squared plus y squared equals 9. So here the radius is 3. So r is belongs to 0 to 3. Is it? As you see, let me use another color. This one from here to here. This is 3. Okay, it's r. R is from 0 to 3. This is r. How about theta? As you see, it's rounded. That means it's from 0 to 2 pi. It's from 0 to 2 pi. Okay, from 0 to it's one round. So theta belongs to 0 to 2 pi. And here r squared equals x squared plus y squared. So if we have any x squared plus y squared, we convert it to r squared, and we leave z to be the same as itself, because we have these elements. We take the integration with respect to z, r, and theta. So it equals to, look, the first integration is with respect to z. Let's say it's dz. Okay. What are the limits of z? Z, it's given. Z belongs to 0 to 2. It's from 0 to 2. Then dr. R is from 0 to 3. We found it. And theta is from 0 to 2 pi. Okay. So dr, d theta. For what? For which function? The function is grad of the vector field. We find this. We find the gradient for the vector field. We find the gradient for the vector field. Okay, grad dot f. That means we say it is partial fy partial x plus partial fy partial y plus partial fy partial z. This is dot. Okay, in the previous, it's the same as the previous example when we found the. Sorry, in the previous example, we found the gradient of phi. When you find gradient of a function, it becomes a vector. It's a vector. Gradient vector of a function is a vector. but here it's the dot product of gradient and a vector. It's a vector. So we must get here, we must get a function in dot product of any two vectors is a function, is a scalar function. This equals to the triple integral from 0 to 2, 0 to 3, 0 to 2 pi. For gradient, the gradient is partial by partial x, I, plus partial by partial y, j, plus partial by partial z, k, dot f is given, which is x cubed plus y cubed, x cubed I, plus y cubed j, plus z squared k. This is dz, dr, d theta. Now we find this dot product. We multiply I component to I component, j to j, z to k to k. This equals to the triple integral from 0 to 2, 0 to 3, 0 to 2 pi. For partial f by partial x, to find this one, yeah, we find the partial derivative of this component with respect to x, which is 2x, so 3x squared plus 3y squared plus 2z dz dr d theta. We now convert x squared plus y squared to r squared, so you get 3r squared. This equals from 0 to 2, 0 to 3, and 0 to 2 pi. For 3r squared plus 2z dz dr d theta. Now we find these triple integral. First, with respect to z, we get 3r squared z plus z squared. This equals to, here we take the first integration, which is with respect to z, from 0 to 3, from 0 to 2 pi. We get 3r squared z plus z squared from 0 to 2 for dr d theta. And the sequel here we replace z by 2, then by 0. If replaced by 2, we get 6r squared plus 4 dr d theta. Then we take integration with respect to r. We get 2r cubed, 2r cubed plus 4r. When r from 0 to 3 d theta, we still have an integration with respect to theta. And this equals to the integration from 0 to 2 pi. If we replace r by 3, we get 54 plus 12 is 66 d theta. Then we take an integration with respect to theta, we get 66 theta. It's from 0 to 2 pi. We get 132 pi. This is the flux. It's 132 pi. Just a moment. Yeah, this is the result. And here at Stokes theorem, we have no examples about Stokes theorem. We just have the rule. It's similar to the previous one. When it says use Stokes theorem, or it says, if it says find the integration over this closed curve. As you see, if you see this symbol, this symbol integration, here you must use the Stokes theorem. The Stokes theorem is this one. Here we find the cross product of gradient with the vector field, then dot product with the normal vector over ds. Over sigma. This is double integration. Here, this is the rule of Stokes theorem. You should know the rule and you just can apply to the examples. It's similar to the previous ones here. You should first find this cross product, then finding the result of this cross product, the dot product with n, then find the double multiplication. That's all. Okay, that's the end. So we have nothing else. We finished all these subjects.